As Ben mentioned, my name's Tom Wheeler. I'm a principal developer advocate at Temporal. I've been with the company for about 3.5 years. Although I've spent about half my career as a software engineer, and I've dealt with many of the problems that Temporal solves. And that's really what I want to begin my talk today, explaining to you what that is. So if you've never heard of Temporal before, you're not sure exactly what it is, that's a natural question. What is Temporal? I want to actually start from a different direction. I want to explain why Temporal exists. There's a few trends that have happened over the last 10, 15, 20 years. If you think back a generation ago, every corporation had its own data center. All the computers lived there. Applications didn't really scale like they do today. Things would run on a single computer, maybe a small set of computers, and those computers are right next to each other. It's easy for them to talk. We did our logic through making function calls, but as we needed to scale, we needed to spread things across multiple computers, and function calls became RPCs. We were invoking operations on other machines, and our infrastructure moved to the cloud. Developers started adopting microservices because you have these big monolithic applications that you deployed as a single unit, and there's a lot of risk with that. And anytime there's risk, the velocity slows down because you could have a change in one part of the application that breaks something in an entirely different part of the application. And splitting things into microservices allowed us to allocate resources to the parts that need it. You could give this part more memory. You could give more CPUs to this thing over here. You could have more computers running a particular service. It also gave us flexibility as developers because we could implement each thing in the language of our choice and use whatever database we wanted on the back end. So there's a lot of benefits of moving to microservices, but these two trends have together made pretty much every modern application a distributed system. There's a lot more potential for scalability, but there's also a lot more opportunities for failure because instead of invoking logic within a single computer, we're invoking logic on other computers, and we're doing that over a network. The other computer could be down, your network connection could be down, the network connection somewhere along that route could be down, and those are the source of a lot of problems that we deal with. Effectively, we're all distributed systems developers now. It used to be a generation ago, that was more of a niche area of computers, but everybody solves the sort of problems that I've described now. So I'm going to give you an example of something that, an application that you may never have thought much about the implementation for, an expense report. At some point, you've probably submitted an expense report. You create the report, you put in your receipts, you put in your expenses, you keep doing that. At some point, you click submit. Your manager gets a notification. They review it. They approve it or reject it. Maybe it gets sent back to you to make some changes. If it's rejected, otherwise it goes to accounting. They reimburse it. You get a notification for approval. So this involves a lot of different systems that have to integrate together, and they all have to be running for this thing to take place successfully. If you were implementing this, you'd probably have an application database to store the information. You might have message queues to have different parts of the system communicate with one another. You might have a cron or scheduler that is sending notifications. So you have a lot of pieces of infrastructure, and all of those have to be up and running and functioning the way that you expect. Also, this involves multiple people. It's a mix of automated and human-in-the-loop sort of things, manual processes. And it also, the entire process could take multiple days, even multiple weeks from end to end. And during that time, things could crash, things could fail. And so you've got to make sure that your applications are reliable. So let's drill down into just one part of that, the reimbursement. A reimbursement might seem like a single operation, but it's actually two operations. You've got to take the money out of the company account and put it into the employee's account. Both those things have to happen, and they both have to happen exactly once. So this is a distributed system. Here I have a function to do that reimbursement, and it creates a client for one bank's API, the employer, another client for the employee's bank, and then it does a withdrawal, it does a deposit, and then it generates a confirmation message. This seems so easy, right? 6 lines of code. How hard could it be? Well, this is the joy of being in development, where you don't have to solve real-world problems. But let's take a descent into the madness. So the problem that you're going to encounter first probably is that you can't make a connection to one of those banks because either the service down or the network is down. So you say, I've got it. I'll implement support for retries, and I'll just keep making requests until one of them finally goes through. So then your code goes from 6 lines, it's now quadrupled in size, but Now you can survive, an outage of the network or the service. The next thing you might encounter is that the service returns an error. Maybe you were able to withdraw the money and you go to deposit the money and it gets rejected, or something occurs, you can't deposit the money. So now the account balances are off. You've got to compensate by putting the money back where it came from, effectively unrolling or rolling back the transaction. And so when you add support for that using the saga pattern, which sort of is a common way of undoing things in a distributed system, now your code gets even bigger and more complex. Another problem you might encounter is that you successfully make a request, but you never get a response back. Well, you can't wait around forever. You've got to, at some point, fail that request and try again, or perhaps call a different system or something, or alert a human that they need to take action. So the next thing you do is, okay, I'll add support for timeouts and then fail the request and don't get a timely response. So you do that, and now your code looks like this. So maybe you can recognize this. Maybe this has happened to you. Nobody sets out to write code that looks like this. Everybody sets out to write code that looks like this. But as you get into production and you encounter problems and find solutions for them, your code becomes more complex. So let's just compare the before and after. We started off simple. As we got into production, we encountered problems. We tried to mitigate those problems. And now our code is really complex. And you think, okay, we've solved all the problems. Everything's cool. This application runs reliably. But does it? No. There's still a big problem here. So I'm just showing kind of an excerpt of that larger code sample. But what if you do the withdrawal, but before you make the deposit, the application crashes? And it could crash due to a defect in your code, a bug in a library dependency, a kernel panic in the operating system, a power outage, hardware failure. There's a lot of things that could cause this code to crash in the middle of processing. And it might seem like a 1 in a million thing, but I bet all of those things have happened to you at one time or another. And when you're operating at a certain scale, these things happen all the time. Everything fails all the time. So if the code crashes between these steps, you've got a problem, and it's a hard problem to solve. So I want to introduce a term, durable execution. Has anybody ever heard of that term? Few of you? Okay. So I'm going to do a demo here, and what I'm going to show you, I think the best way to understand the concept of durable execution is to compare normal execution to durable execution. And I'm going to do that by way of a very simple program that I wrote in Java. It's not terribly involved code. It's probably one of the simplest Java programs you could write. I've just got a class that's got a main method that calls this method called count2. I pass in a number. And so in the implementation of count2, I've just got a for loop. It's going to count up to that. And in each iteration, it's going to print out the current number. So we've got some application state there. That current count is the state of our application. And then it's going to sleep for 1 second. And in Java, the API is that you specify the duration in milliseconds. And I just want to mention what an unusual thing that is, or what a notable thing that is. For decades, I've been doing Java for a very long time, and for decades, the only way that you could specify time was in milliseconds. Maybe 10 or 15 years ago, they added support for nanoseconds, so you could get even shorter amounts of time. But thread.sleep was never meant to sleep for a day or a month. That would be crazy. You can't expect the program you start now is going to be running a month from now. So I just want to point out, having long-running programs like this that pause for long durations is not something that the language designers intended. And the same is true for a lot of other languages. So I'm going to run this now. And it's going to print out 1, 2, and so on. It gets to the end. Okay, so now I'm going to do it again. And I'm going to kill it. It printed out 2. So when I rerun it, what number is it going to display next? 1. Right. You know that because you are developers. You understand how computers work. And, but if you ask somebody that doesn't know anything about computers and you said, what's the next number that would come out? They might say 3. That's what you would expect to happen if you don't know anything about computers. They don't know about the loss of application state that takes place when a program terminates unexpectedly. But I'm here to tell you that they can work that way. And so let me show you that. That is durable execution. So compile and run. It prints out 1, 2, I kill it. Start it up again. Takes a moment to recover the state. 3, 4, 5, and it prints it out. And so that very simple idea, the fact that you can kill a program and then have it resume from where it left off rather than start over from the beginning, changes your world as a developer. And so let me talk more about that. Durable execution is crash-proof execution. It's made possible by an abstraction that's provided by a durable execution platform. And Temporal is an example of a durable execution platform. In Temporal, that abstraction is called a workflow. And I want you to set aside any baggage you have about the term workflow. You might be thinking about drawing little pictures of, what your code should do. In Temporal, you define workflows through code. We support Java, Go, PHP, Python, Ruby, C#. I may be leaving, I'm probably leaving out a language. The community has created an SDK for Swift. There's one for Clojure. So there's a lot of different languages you can write this in. And you can actually mix and match those languages together in a single application. So you can have a Java that calls into Ruby, for example, or vice versa. So a workflow is nothing more than a function or a method, depending on the language, that has durable execution. Once it begins execution, it's guaranteed to continue running even if it's killed. It's able to sort of reconstruct the state and then resume the execution and continue on. So let's look at what's happening behind the scenes in that early example. This is the non-durable execution, the normal execution. The computer starts up, we print out 1, we print out 2, bang, I killed it. That's where it ends. The story ends right here. The process terminates, execution came to an end. That's because normal execution is bound to a single process that's running on a single machine. And when that process exits, we lose the application state. We lose the program counters. We no longer know which things have already run nor what's left to run. With durable execution, it essentially virtualizes this so that execution can span a series of processes, each of which could potentially run on a different machine. And that means you can withstand hardware failure as well. So here's what it looks like with durable execution. We start up, 1, 2, 3, program dies just like it did before, but that's not the end of the story with durable execution. Process number 1 terminated before the 3rd step completed, but it resumes in a new process, reconstructs the state, and then continues on from there. So it prints out 3. Let's say it dies again. And this time, let's say it dies due to a hardware failure. So what happens now? Reconstruct the state on a different machine in a new process. Then it continues, prints out 4, prints out 5, and at this point, execution is complete. So the summary is in this example, we began in process 1, we made a little bit of progress. In process 2, we made some more progress, and then we finally completed in process number 3. So we have an execution that spans multiple processes over time. The physical representation of what took place here is below the line. Sure, it ran in 3 different processes, but from your perspective as a developer, it doesn't matter. And the reason it doesn't matter is because this is what the developer experience is. Everything ran. You don't even see or know or worry about the failures. I mean, you can find them if you want, but they don't affect you. And because they don't affect you, you don't have to write a bunch of code to handle all this. You don't have to write code to manage application state. You don't have to write code to manage what happens in case of a crash. It all happens automatically and transparently to you as a developer. So durable execution, I think, is a revolutionary idea. It's a really simple concept that your program can survive these catastrophes, but the impact is profound because it makes your application more reliable. That's obvious, but what's less obvious is that it allows you to focus on the goal. You focus on the happy path. You code for success, what you want your program to do, instead of spending all your time anticipating and trying to mitigate all the problems that could happen along the way. As a result, you have applications that are faster to develop and easier to maintain because your business logic is not surrounded by this complexity of error handling and state management and things like that. So what is Temporal? It's an open source durable execution platform. It automatically maintains the state of your application. It enables your applications to recover from crashes as if they never even happened. So you don't have to worry about them as a developer. In the same way that you don't have to worry about, what order do packets arrive in on the network. The operating system takes care of that. It abstracts all that away from you. And the same way that Temporal abstracts away crashes and things like that. It also offers support for retries and timeouts, so that complexity of the code that I showed before, when a service goes down or the network goes down, you have those benefits automatically. So you can survive failures and outages of services that you're calling into. Ultimately, it improves developer productivity by making your applications easier to develop, scale, and support. So now I want to show you a demo, another demo. This time it'll be with Stripe. Oh, by the way, let me introduce the Temporal Web UI. The Temporal Web UI allows you to see every execution that takes place. You can see the ones that are running right now. You can see ones that have run in the past, and you can know exactly what happened at runtime. So I'll just show you me counting to 5. So you can see right there, it's in the timeline view, print 1 and sleep, print 2 and sleep. Then there's this delay because I killed it right after 2. It reconstructed the state, and now print 3 and sleep, print 4 and sleep, print 5 and sleep. And down in this table, we can see everything that took place. Information in this table will tell us, for example, like what machine this ran on, exactly what time it started, what time it finished. We have all the information we need if we need to debug something. So that's very helpful. Okay, so this is on Temporal's community GitHub. There's a scooter demo there, and I'm going to run that. This is an application that uses Temporal. So it's written in TypeScript, and there's 3 parts of it. There's a back end, which is the Temporal code, an API, and then a front end. And the front end knows nothing about Temporal. The front end calls to this API, and the API calls Temporal. So all the code for the Temporal stuff, let's just see here. There's only a few hundred lines of code, a lot of which don't even have anything to do with Temporal. So if we're just to look at the workflow itself, it's 150 lines of code in the workflow itself. So the workflow is doing all the orchestration for what I'm going to show you. And think about like a Lime scooter or a Bird scooter or something like that. So I'm going to log in and unlock the scooter, and it's going to start the ride. And so now I'm riding through town, and it's racking up. If you look in the lower left, you can see it's using these tokens. This is using Stripe's usage-based billing. So in my Temporal code, I'm making calls to Stripe's APIs, and I'm doing billing. And I'm charging based on how far someone's riding and how long they're riding and things like that. And so let's just say we're going to end the ride now. And there we go. And if we look at the workflow in the web UI, we can see everything that took place. We found the Stripe customer ID. We begin the ride. We add some distance, a charge for that. We post the distance charge to Stripe. Same thing for, we're adding time charges as well. And so we can see everything that took place all along the way. Let me show you another example here, and we'll dismiss that. And I'm going to choose scooter 1, 2, 3, 4, Maria, example.com. And so now we're trying to start the ride, and it says, oh, ride initialization is taking a while. Please wait a moment. And if we go into the web UI and look what's happening, we see this red line here, and this red line will tell us exactly what's the deal. We can see network error while attempting to contact Stripe. Now, Stripe's not really down. Stripe is a very reliable service. This is something I did in a demo to simulate a network error. But if you're calling some other service that's not as reliable as Stripe, if you're trying to query a database and that database is offline, if you're trying to write to a file, the file system's full, you may encounter some other problem. Well, in this case, it's just retrying. It's automatically retrying that call. And we can see from that number right there, 4, it tried 4 times, and on the 4th time it was successful. And so now if we switch back, and we can ride. So we had this network outage, and it didn't wreck the program. There was a delay, but now we're able to ride. Show you another example here real quick. And let's say we're going to put in test at example.com, which is not, there's no account associated with this. So we try it, and in this case, the workflow that manages the ride fails. We wanted it to fail because this is an invalid rider. So we have control. We can make things fail when we want to, but when that happens, we can see exactly what happened. That tells us exactly what line of code happened, what took place, and we have everything we need. One last example, and I'm going to use 1, 2, 3, 9. Oop. Put in a valid email address. Okay. So now if I go back to the web UI, there's another one running. And this is failing. Let's see what's going on. So if I just click this, it'll tell us exactly, oh, invalid scooter ID 1239. Wonder why that's invalid. Well, let's go look at activities.ts line 56.3. And I'm going to kill the back end for a moment in this very terminal. I'll go look at activities. And right here, I can see there's a bug. It's got a regular expression that's trying to check the scooter ID, and instead of doing 0 through 9, it does 0 through 8. So it's a typo. So I can comment that line out, and I'll put in that one, which has the correct regular expression. So I fixed a bug in my code. This has nothing to do with temporal, but I fixed a bug in the logic of my application. And now I'll just start that back end again. So I killed the program, to be clear. And now I can ride. So if we look back at the history, scroll up, close this, there. We can see that sort of red and green line. Those red lines are telling us that we had a problem at that moment, but it got resolved, and now everything is happening after that. So I'm able, what I just demonstrated is I fixed a bug in live running code. And you can do that because of this durable execution. The program was running, but it had a problem. And when I fixed that problem, it retried, and the problem, it skipped over that because the problem's not there anymore, and it's able to continue successfully. So that's Temporal at a glance. Again, it's a durable execution platform. It's open source. It has support for all the common languages that people typically use, and it has this web UI that gives you observability into what your application is doing at all times. And finally, I didn't show here in Stripe, there's the usage-based billing. So these are the tokens that I've consumed. It's all showing up right there in the Stripe dashboard. So you can connect to Stripe and any of the services that they provide APIs through, or any other service you want to use. That's all stuff you can do from a temporal workflow. You just write the code in whatever language you want, and you get the reliability and the developer productivity that I described.